NASA and China are stunned. SpaceX is proposing something revolutionary, landing its colossal Starship on the Moon without any landing legs. This daring idea could cut weight and simplify missions, but it also defies decades of lunar engineering wisdom. Can a rocket this massive stay upright on the Moon's uneven surface? The stakes are enormous, and the world is holding its breath to see if it can actually work. A history of lunar missions. The story of humanity's journey to the Moon is one of ambition, risk, and incredible ingenuity. The first major leap came during the Apollo program, when humans set foot on the lunar surface for the first time. Apollo 11 in 1969 saw Neil Armstrong and Buzz Aldrin leave their footprints on the Sea of Tranquility, and the missions that followed brought back rocks and soil that would transform our understanding of the Moon forever. These early missions proved that landing humans on another world was possible, that we could survive there for brief periods, and that the Moon was not just a distant, untouchable object in the night sky. The Apollo missions became the blueprint for lunar exploration, inspiring generations of scientists, engineers, and dreamers. Decades later, after a lull in lunar activity, space agencies around the world reignited their ambitions. China emerged as a major player with its Chang'e missions. Chang'e 3 in 2013 was a milestone, carrying a lander and the U-2 rover to explore the Moon's surface, demonstrating that precise soft landings were achievable without the massive budgets of the Apollo era. Later missions like Chang'e 5 brought lunar samples back to Earth in 2020, marking the first return of Moon rocks in over 40 years. The most recent Chang'e 6 mission took things further, returning samples from the far side of the Moon, a feat that had never been accomplished before. Each mission highlighted China's growing technical prowess and its careful strategy of combining exploration with scientific goals. Other nations have joined the Moon race as well. India's Chandrayaan-3 successfully landed near the lunar South Pole, a region of immense scientific interest because of its frozen water deposits. These missions demonstrate that the Moon is no longer the domain of a single superpower. They reflect different approaches, engineering solutions, and political ambitions. Every landing teaches lessons about navigation, communication, and survival in an environment that is harsh, unpredictable, and unforgiving. The significance of these achievements extends the immediate science. They prove that the Moon is reachable again, that human and robotic explorers can work together, and that each new mission pushes the boundaries of what is possible. Yet, as space agencies chart familiar paths, a private company is now proposing something radically different and surprising. SpaceX's bold pitch to NASA. SpaceX has once again shaken the space world with its audacious vision for returning humans to the Moon. At the heart of this plan is Starship, a massive spacecraft designed to carry both cargo and astronauts Earth's orbit. Starship is central to NASA's Artemis program, and SpaceX won the Human Landing System contract for Artemis III, tasked with safely delivering astronauts to the lunar surface. The company's proposal promised innovation, cost efficiency, and the potential to radically change how lunar landings are approached. SpaceX's plan stands out because it embraces what the company calls a simplified mission architecture. Rather than relying on complex systems and heavy landing legs, the design focuses on reducing mass and trimming unnecessary complexity. This approach could allow Starship to land more efficiently, carrying more cargo or fuel while potentially skipping traditional landing legs or redesigning them entirely. By streamlining the spacecraft, SpaceX argues that missions could be faster, cheaper, and less prone to failure. The boldness of this plan reflects SpaceX's overall philosophy: push engineering boundaries while minimizing constraints that slow down progress. The timing could not be more critical. NASA faces growing pressure to accelerate its return to the Moon. Delays in Starship development and concerns about schedules have added urgency to Artemis planning. NASA must balance speed with safety, ensuring astronauts are protected while meeting ambitious timelines. SpaceX's proposal offers a tempting solution, promising to reduce weight and simplify operations, which could help NASA meet deadlines while keeping Artemis on track. However, this idea forces NASA to rethink how it evaluates risk. A lander without conventional legs changes the game entirely, challenging decades of engineering assumptions. Internal debates now swirl around safety, stability, and whether a radically different landing system is acceptable for human missions. Contracting strategies and oversight could shift as NASA weighs the benefits of innovation against the risks of untested designs. Yet the most pressing question remains unresolved. Landing a multi-ton spacecraft without legs on the Moon presents enormous technical hurdles. How will Starship remain stable on the uneven, dusty lunar surface? What trade-offs in engine thrust, landing approach, and surface interaction must engineers accept? Solving this puzzle could unlock a new era of space exploration or expose risks that even SpaceX may not have fully anticipated. Engineering Starship for a legless landing. SpaceX's approach to a legless Starship landing is the result of meticulous engineering and collaboration. The company assembled a team of experts from diverse fields, including structural engineering, propulsion, and robotics, many of whom had worked on previous successes like Falcon 9, Crew Dragon, and prior Starship prototypes. Lessons learned from earlier missions, such as rapid prototyping, precision landing, and orbital refueling, provide a foundation for tackling the unprecedented challenge of landing a massive spacecraft on the Moon without traditional legs. Redesigning Starship for a legless landing requires rethinking its very structure. Engineers would need to adjust the mass distribution, reinforcing key areas of the hull to withstand the forces of touchdown. Fuel tanks might need resizing or repositioning to keep the center of gravity optimal, and overall structural integrity must be ensured to handle the stresses of vertical descent and sudden engine throttling. Every component must work together to absorb impact while keeping the spacecraft upright on a surface that is far from level. Stability on the uneven lunar terrain is a major concern. Without landing legs to spread the load, Starship could tip if thrust vectors are slightly misaligned or if it lands on a slope or loose regolith. SpaceX may explore advanced sensor systems, real-time engine throttling, or small auxiliary thrusters to counterbalance tipping moments. Sophisticated algorithms could allow the craft to adjust instantly during descent, effectively hover balancing until it touches down safely. Preliminary testing is critical. SpaceX has conducted drop tests and used regolith simulators on Earth to mimic the Moon's dusty, uneven surface. These experiments help engineers understand how Starship behaves under extreme conditions and allow iterative refinements of landing strategies before committing to an actual lunar descent. Another key factor is in-orbit refueling. By topping up Starship's tanks before heading to the Moon, engineers can reduce structural hardware weight while ensuring sufficient propellant for landing and return. This trade-off between fuel and structure is delicate but essential for making a legless landing feasible. Each kilogram saved in hardware can be allocated to more fuel or additional safety systems. Solving one piece of the puzzle is not enough. The entire journey must work seamlessly to make a legless lunar landing a reality. NASA's reaction, risk, contract, and competition. NASA is watching SpaceX's legless landing proposal with a mix of intrigue and caution. The agency is well aware that landing a massive spacecraft without legs has never been attempted before, and the risks are significant. Engineers worry about Starship's ability to remain stable on uneven lunar terrain, the reliability of in-orbit refueling, and whether the spacecraft systems can handle the stresses of a touchdown without traditional landing structures. Even small miscalculations could have catastrophic consequences, so NASA's technical skepticism is grounded in decades of lunar experience and safety protocols. These concerns are influencing contract decisions. Reports suggest that, due to delays in Starship development, NASA is considering reopening the Human Landing System contract to other competitors. This move could introduce rival companies with alternative designs, creating a competitive environment where speed, innovation, and reliability are all weighed against each other. NASA must balance the desire for cutting-edge technology with the necessity of meeting Artemis program milestones safely. Timeline pressures add another layer of complexity. Artemis aims to return humans to the Moon quickly, and any slippage in Starship development could push schedules back. A legless design, while bold, introduces uncertainties that might jeopardize the carefully planned sequence of launches, refueling, and lunar operations. Every day of delay has ripple effects, potentially affecting astronaut readiness, supply missions, and scientific goals. NASA must calculate whether the benefits of a radical new design outweigh the risks of schedule disruption. At the same time, engineers and planners are exploring alternative strategies. Smaller landers, hybrid designs combining traditional and simplified landing systems, or different mission profiles could serve as fallback options if the legless Starship proves too risky. Each alternative comes with its own trade-offs in cost, capability, and schedule, but they offer NASA ways to keep Artemis on track while mitigating the dangers of an entirely untested landing method. Yet while the United States debates its next move, eyes are on the global stage. China has already demonstrated significant lunar capability, from sample returns to far-side exploration. Every decision NASA makes is not just about engineering and risk management but also about maintaining leadership in the moon race. The question now becomes, can the United States innovate fast enough to stay ahead, or will other nations seize the lunar advantage? China's lunar strategy and the space race intensifies. China's lunar ambitions have steadily grown over the past decade, combining careful planning with technical innovation. The Chang'e program has been at the center of this strategy, beginning with Chang'e 3 in 2013, which carried a lander and the U-2 rover to explore the moon's surface. This mission proved that China could achieve precise soft landings and conduct sustained surface operations, marking a turning point in global lunar exploration. The success of U-2 and subsequent robotic missions laid the groundwork for more ambitious goals, establishing China as a serious player in the space race. Building on this momentum, China achieved a major milestone with the Chang'e 6 mission, returning samples from the moon's far side. This was the first time humanity collected material from the lunar far side, offering unprecedented scientific insights into regions that are otherwise hidden from Earth. Its scientific value: the mission demonstrated China's growing mastery of landing, sample collection, and return operations under complex conditions. It also signaled strategic intent, showing that China can explore areas that others have not reached, reinforcing its position in lunar geopolitics. Looking forward, China has laid out ambitious plans for a manned lunar landing and the construction of a research base on the moon. Discussions of reusable landers or Starship-like vehicles suggest that the country is not only focused on exploration but also on sustainable lunar presence. By developing these capabilities, China aims to combine scientific discovery with long-term strategic advantage, creating infrastructure that could support astronauts and robotic missions for years to come. The entrance of SpaceX's legless Starship concept adds a new layer of complexity to this global competition. On one hand, China may see it as an opportunity to learn from another bold engineering approach. On the other, it represents a potential threat. If successful, a legless Starship could drastically reduce costs and timelines for lunar access, potentially leapfrogging traditional approaches. Chinese planners are likely evaluating how this innovation could alter mission architecture, logistics, and their own timelines for lunar presence. Even as the competition heats up, questions remain about the feasibility of Starship's legless landing. The concept pushes the boundaries of engineering, stability, and safety in ways that have never been tested on the moon. While ambitious, it carries enormous risks. Please like and subscribe channel.